Okay, so your first impression, since a path integral is to carry out a path integral, you have to do an infinite number of one-dimensional integrals. You might think that defining path integrals is hard, and indeed it is. In fact, in quantum field theory, in most situations, we do not have a good definition of exactly what the path integral is. We don't have a rigorous definition for path integrals. But one thing that you can do is you could choose to work on a lattice. So if you work on a lattice, you know, your space-time, events in your space-time are indexed by labels x and t, which are continuous, but you could choose to go to the lattice. So let me just put here lattice. And then you would have a discrete set of points and a discrete set of times. And if you work on the lattice in a box, then in fact, you have only a finite number of lattice points. And that means, for example, if you have a field will assign a value to each lattice point. And when you're doing the path integral, you would have an integral over the value of the field at each lattice point. So it would actually turn into a finite number of integrals. And this is one way that you can actually do calculations in quantum field theory using the path integral. And this is called lattice field theory. It gives good results. And I would say it's pretty compelling evidence that the path integral really is a correct description of nature. I should also mention, if you go and look in various textbooks, you'll see what is often advertised as a derivation of the path integral. And what you'll do is you will start off, say, in quantum mechanics, you'll discretize time, break time up into a whole lot of a discrete instance, and then insert a whole set of position eigenstates at each time and manipulate the resulting expression. And what you get out at the end of the day does look like the path integral formulation of quantum mechanics. If you wanted to make something like that rigorous for quantum field theory, the details, the burden of the proof would be in showing that all of these things are well defined when you take lattice spacings to zero, and they're independent of the way you discretize, so that you really do get a good continuum answer. And that's what nobody has really managed to do. So if nobody's managed to do that, you might be a little pessimistic, and you might think, well, how on earth are we going to be able to calculate our path integral? So let me tell you what our approach is going to be. And let me just rescue the formulas that I want. Here they are. So let's see if I can do this. Duplicate. So far, so good. Let's move it down to where we're working. Great. So this is the integral that we want to do. Let me just get rid of stuff that we don't need. This is the integral that we want to do. And to start at least, so I'm just going to call it I, okay? You know it's a correlation function, or, well, we'll calculate the integral and see if it really is a correlation function. And we want to start off doing it for the free theory because somehow we think the free theory is going to be simpler. That's a very reasonable expectation. And so that's the action we'd like to do it for. And what I'm going to do is I'm going to learn how to do the path integral by studying a simpler integral that I do know how to do. And the simpler integral is this one. It is, oh, sorry, let me change to a pen. Good. Oh, okay. Good. So the integral that I do know how to do is this one. In is equal to an integral from minus infinity to infinity dx. So it's a one-dimensional real integral that I'm definitely okay with doing. E to the minus alpha over 2 x squared x to the n. And why did I choose to do this? Well, take a look. There's a few things, okay? So first of all, notice that if we look at this action, the action is quadratic in phi. Okay? In the integral that I'm looking at, I've chosen the exponential to be quadratic in x. Okay, so that's an important point, and we'll see that that's actually useful. And the structure that we're going to mimic depends crucially on the fact that things are quadratic. Then secondly, look at the integral we want to do. We have phi's in the integrand. In fact, we have n phi's in the integrand. And that's why here I put n x's into the integrand. Okay? So far there's only a superficial similarity, but you're going to see that really this is the integral that we need to study to really figure out how to do the path integral. And now let's start with the simplest possible situation. So we're going to try to evaluate I naught. So I naught, this is the case where there's no x's sitting down below. So I naught runs from minus infinity to infinity dx e to the minus alpha over 2x squared. Now, when we start solving this problem, one of the tricks that you can use is dimensional analysis. You know dimensional analysis so well that you're not going to make a mistake using it. So it should be a trick that you should use as much as you possibly can. So let's say that we assign dimensions of length to x. So I'm going to imagine that x is a length. Well, the exponent, so the minus alpha over 2x squared, must be dimensionless. Okay, this is true for any non-trivial function. You know, if I've got e to the minus alpha over 2x squared, and I do a Taylor expansion, this is 1 minus alpha over 2x squared. Then we'd have plus 1 over 2 factorial alpha over 2 squared x to the 4 minus, and so it would continue. And this expression only makes sense if each of the terms that I'm adding up has the same dimension. The first term, the 1, is dimensionless, so the alpha over 2x squared, well, that had better be dimensionless too, okay? So this is why the minus alpha over 2x squared has to be dimensionless. Good. If that's the case, so let's just start summarizing a few things. Well, we've said that x has dimensions of length. If alpha times x squared is going to be dimensionless, that means that alpha must have the dimensions of length to the minus 2. So we've got length to the minus 2 from alpha times by length squared from x squared. That's dimensionless. Great. And then if we look at I naught, well, the dimensions of I naught is equal to, well, we've got the exponential. That's obviously dimensionless, but we've also got dx. So I naught is going to have the same dimensions as dx, and dx is a length. So I naught is a length. And if we look at all of the parameters in the problem, the only parameters we've got is alpha. So when we've finally done the integral for I naught, it must be a function of alpha. So I have to build something with the dimensions of length out of alpha, which is a 1 over length squared. And that means I naught has to be equal to, well, 1 over alpha, that would be length squared. So 1 over square root alpha, that would be length. So that's the right dimensions. But the numerator here, well, I don't know what that is. That's going to be something that's dimensionless, some number. So let me just call that C. And I'm going to have to work out what C is. I don't know what C is. Now, I naught, so I naught is some number over the square root of alpha. That looks hard to get. It's hard to get a square root. You know, hard to get a square root. That's not easy. Oh, sorry about that. Internet in China is not the best. Okay, so it's hard to get a square root. So instead of trying to calculate the value of I naught, it's much, much better to try to calculate the value of I naught squared, because I naught squared will be some number squared, whatever it is, divided by alpha. And it's much easier to get a 1 over alpha than it is to get a 1 over square root of alpha. Okay, good. So let's look at I naught squared. So I naught squared would be an integral from minus infinity to infinity dx e to the minus alpha over 2x squared times by, well, exactly the same thing. An integral from minus infinity to infinity dy e to the minus alpha over 2y squared. Well, you know, x and y are independent variables. By the way, I gave the both integrals different names so that I don't mix up the dummy integration variable names. But these are independent variables, so I can think about this as just a two-dimensional integral of this type. And if you were to walk into the room and I showed you that integral and said, look, this is the integral I've got to do you have any advice? Well, I'm sure the first thing you'll say to me is, well, it depends only on x squared plus y squared. So why don't you move to a radius and an angle? And we'll do that in a moment.